Hi, everybody. Welcome back to the Feynman technique. Today, we are going to be deriving the uh, solution to the Basel problem. So, the Basel problem asks for the exact sum of the reciprocals of the squares. And it stumped mathematicians for a long time until Leonard Euler finally solved it in 1734. And we're going to solve it the way he did. Okay, so first we're going to look at the Taylor series representation for sine x. This should be familiar for anybody watching this channel. If you're watching this channel, it's kind of assumed that you know things up through, we'll say, calculus BC. All right. And now we'll notice that sine x has zeros at, well, 0 and also plus or minus n pi. So our sine x function is going to have zeros there. That's important. Okay. So if we know some function has zeros at n pi, we can express it as a product as long as there are zeros at n pi. And we have zeros at n pi in this product, as you can see. We'll get a 0 here if we plug in positive n pi, and we'll get a 0 here if we plug in negative n pi, and we'll get a 0 here if we plug in 0. So this is the infinite product representation for sine x. That's probably new to some of you. But yeah, sine can be expressed as an infinite product or an infinite sum. All right. So let's see. Continuing from here, we can divide both sides of sine x is equal to this by x. And we get this is equal to this. All right, great. So now what do? Let's take a look at the coefficient in front of x squared in our Taylor series representation. What did that look like? Well, this is the Taylor series representation, and it keeps going on forever. And you'll notice that the only thing that contains an x squared is this. This is the x squared term, and its coefficient is negative 1 over 6. All right. Now let's look at the coefficient in front of our x squared term in our product. What is that going to be? Well, how are we going to get an x? It's a little bit more difficult because now we're multiplying things together, but let's think about it. If we keep multiplying things of this form together forever and ever, there's only going to be one x squared term. You can only get an x squared term by multiplying this term by, and then all the other terms you have to choose for the next thing in your product has to be 1. All right. So basically, the coefficient in front of our x squared terms in our product is going to be this thing right here. That is the coefficient. So we can set that equal to the coefficient that is in front of our x squared term in our sum representation. In other words, just like this. And if we match that up, we see that the sum of the reciprocals of the squares has to equal pi squared over 6. All right, we're not quite done yet. As you'll notice, we're only on step 8 of 14. It looks like we solved it. Well, we did, but there are two other sums that you can derive from this one. And so let's do that. All right, let's examine the sum of the even squares. Well, that's going to be equal to this, right? The sum of the evens is just, it can just be represented by this. We just let our thing that's being squared be equal 2 times an integer, right? Then we can rewrite it like this, and finally rewrite it like this. So the sum of the even squares is exactly 1/4 the sum of the squares. All right, so again, the even sum is going to be equal to 1/4 the sum of the reciprocals of the squares. So that's pi squared over 24. All right, so now we have the sum of the evens. Well, let's notice that the sum of the odd is equal to the sum of all of them, which we know is pi squared over 6, minus the evens, which we know is pi squared over 24. So that means that the sum of the odd squares is pi squared over 8. And we've got one more. So now that we know the sum of the odds and the evens, let's take a look at the sum of the alternating squares. All right, well, that's going to be equal to, well, the sum of the odds plus the sum of the or minus the sum of the evens, right? Okay, well, we know the sum of the odds and we know the sum of the evens. Therefore, the entire sum is pi squared over 12. So again, the sum of the alternating reciprocals of the squares goes to pi squared over 12. All right, guys, I hope you enjoyed that, and we'll see you next time.